Yeah, howdy, folks. I'd like to I shared with you recently the idea of a vibrant universe, and I made some calculations, which I try to show you right now, and I hope you understand. I hope this video makes sense because the microphone of this video or this camera is not so good. So I hope it makes you can hear me. But I'm going to show you what I've done, and I'm going to show you some graphs in which I can show you what I mean. Okay. Okay. What I've done here is, like I said, it is all about waves and fluctuations. What I've done is, if you see these numbers here, the x part, and this here is the frequency part. So this tells you something about the frequency, and this is just very simple. It's the sinus of the position times the frequency. So that's basically it. And I did it for a lot of numbers, or for a lot of positions and a lot of frequencies. And what I simply did is added them up. As you can see here, I simply added them up. Just adding these up, and then you get this. And then I squared them. So the sum of this, and I squared it, and then divided by, in this case, by a number of 2. Let me increase the... Oh, here you can see it more better. Home. So this is the sinus of the position times the frequency, and what I've done is here make a sum of it. I squared it and divided it by 2 to get a nice view. And in this case here I subtracted 10 minus this number. I did that for a purpose. And here we got the graph of it. This is what I mean. What you see here, these are the added sinuses all together with all kinds of frequencies, and you see a periodic kind of pattern emerging from it. Maybe I can enlarge it. Yep, I can. Here you see a fluctuation, and in between, and that's what we're interested in. These very bluish parts are moving parts in space-time. So, and here in between there are some quiet places, and of course this bluish part is very big, so this is moving very rapidly. It's fluctuating very rapidly, and these are also fluctuating highly, but these are fluctuating less. So in these points you can expect, these low points, you can expect that there is relatively quiet. And where there is relatively quietness, you can expect for matter to gather. What I did is 10. Well, this is 10, and then 10 minus these fluctuations. So you see here at the high top peaks there it's low, and there's a low there is relatively quiet, the green line, the thick green line. So where there is the number is low, there is less matter to expect it, and a large empty space. And here where on the tops of these of this graph, mass can be expected. If you have a lot of fluctuation, then the less mass is going to gather. But if you have high silence, if the silence is bigger, then where's less movement, then you can expect masses on top of the over there. Or in the reverse, if there is a high frequency, a high movement, high vibrationals. Here, this is empty space. These are empty space regions, like this and this and this, and so on, and this. Empty space regions where there's a lot of fluctuation, and in between mass can gather, so matter can gather. And well, here it's this could this is very high fluctuating space-time, so you expect a lot of empty space over here, and in between you can expect some mass. This is what it actually meant, and this is of course only in one-dimensional area, one-dimensional graph. But you can imagine that in three dimensions, and the fourth dimension in time included, that there is a very interesting distribution. Now, you see, it's very regular. What we also see, and that's a very interesting part. There was a guy. He's called William Tifft, and he observed what is now known as the Tifftshift in redshift. There was a redshift. We all know what redshift is, I hope. And what he saw, William Tifft, he saw a redshift, and that it's a quantized redshift. Well, if my theory is correct, of course I hope, I don't know yet, but if my theory is correct, well, this may be an explanation why there is a quantized redshift, because it implies that in some spacings there is matter gathered. And that's what you also see in the Tift redshift from William Tifft. That it emerges from this idea that because of space is vibrating and vibrant, that matter is distributed in a way of this. It could be, I mean, of course, these voids, these quiet places could be empty, but for the same token, in a very empty, very here the time is virtually standing still, so that may be the region of a black hole, for example. And here it's more noisy, so it may be a region for a star, a big star. And here this may be a planet or something. I mean, and in between there are regions where there may be black holes and so on. So that's the idea, that due to vibrations of space-time, that dust, like dust is gathering underneath closets where there's less movement, that dust and matter is gathered. And the same happens in big space and in the universe. So that's the basic idea of gravity, that gravity is actually emerging from the vibrations of space-time itself. And one of the things may be that an indication of that may be the Tifft redshift, which is also a quantized form of redshift. And this may be this idea, which I hope, of course, is correct. I don't know yet, but it needs to be tested. I mean, in these regions where the fluctuation is higher, then you expect also a bigger force of the Casimir effect. And so in that may provide also a way of testing this idea of mine, this theory of mine. And the Tifftshift may also be an indication that this idea might be correct. Okay, this is what I want to share with you, and I hope you understand what I'm putting across or try to convey to you. If you don't understand, please ask me questions, and I mean, you can ask me on via the YouTube channel. But this is the basically idea of the vibrant universe. Okay, thanks for watching, and see you next time. Hasta la vista. Bye bye.